Hello students, in this video we're going to solve this second order constant coefficient ODE. In this case we're going to end up with complex roots to the characteristic equation. So the characteristic equation, once again, corresponds to the orders of the derivatives. So I have y double prime corresponds to r squared, y prime corresponds to r because the order and the power are the same. And then y corresponds to 1 because it'd be r to the 0. That's the 0th derivative. So there's our characteristic equation. That characteristic equation can be solved with the quadratic formula and reduces down to, let's see, we have 3 halves plus or minus I square root of 7 over 2. Okay, so those are our distinct complex roots. So we're going to recall that our roots do show up in conjugate pairs, a plus bi and a minus bi. That's where you get the plus or minus I. And the other thing I have to remind you of is Euler's formula, e to the ix equals cosine x plus I sine x. We're going to need that later in the video. So I write the solution. Now you could just leave your solution in this form. Most people don't, but we certainly could do that. You know, c1e and then the one root plus c2e and the conjugate root. We're going to simplify that a little bit. What I'm going to do is I'm going to use the laws of exponents here. If I was adding exponents, that means it must have been a product of the common bases. So I'm going to simplify it that way, and then I'm just going to factor out the e to the 3 halves x from the solution. And once again, we could leave our solution this way. We're not going to do that though. We're going to simplify the stuff inside these brackets here. So what I'm going to do is I'm going to write each of these terms here on the right hand side using Euler's formula. So c1 e to the I square root of 7 over 2 x, that expands out to c1 cos of that argument plus I c1 sine of that argument. And then similarly, c2e to the minus I square root of 7 over 2x is equal to c2 cos of that argument minus I c2 sine of that argument. Now you notice that here on the left hand side of the equal signs, I'm just going to add these together, but that's what we have here, and that will equal, if I just add these two, you're going to see that I'm going to collect like terms. So I'll have c1 plus c2, and I'm going to factor out the common term cosine. Here I'll have ic1 minus ic2, so I'll factor out the I, and I'll have c1 minus c2, and I'll factor out the common sine. That is equal to what we have here. Just inside the brackets, I would need an e to the 3 halves x times this whole quantity here, but this equality means what's inside the brackets here. And then I'm just going to redefine these constants. c1 plus c2, I'm going to call it c1 tilde, and ic1 minus c2, I'm going to call that c2 tilde. I is the square root of minus 1. It's still a constant, so this is an arbitrary constant, but in this case our arbitrary constants can be complex numbers. And now my solution looks like this one here, e to the 3 halves x times, and then c1 tilde cos plus a c2 tilde sine. And I'll leave it to you to verify that this is in fact the solution to this ODE, but this is the form in which most people would write this solution. All right, good luck.